Mass spectroscopy, or MS as it's called, is a technique. It's a spectroscopic technique where we can measure the characteristics of molecules, and we do this by simply converting them into ions. So one particular thing that you should keep in mind is that you will need to knock off some electrons from the molecule in question and manipulate it through electrical and magnetic fields to be able to view those molecules. So anything that's neutral does not show up on mass spectrometer. It has to be charged. Now there are certain essential functions, certain parts of the spectrometer which I want to go over. We have what is called as the ion source. We have the mass analyzer, and we have the detector. Okay, so let's maybe, since pictures speak 1,000 words, let's maybe make a little schematic so you can see for yourself, and then I'll talk about the principle, how exactly it works. We basically have a sample and we maintain it at a low pressure. Let's say the low pressure would be somewhere around, 10 to the -2 torrs or something like that. So pretty low. Atmospheric pressure, as you know, is 760 torrs. 1 torr is 1 millimeter mercury. 1 torr is 1 millimeter mercury, and atmospheric pressure, like I said, is 760 torr. So this is a pretty low pressure, and we have to do this because ions are reactive. They're short-lived, so their formation and the way they would move around should be done in vacuum, should not be done at atmospheric pressure. So usually the pressure that we will use will be somewhere around here, and that can be taken to be approximately close to vacuum. You can go lower than that. You can make it 10 to the power of -5. That's pretty good too. Now, how do we accomplish running the MS? One common procedure of ionization is that what you do is you take a high energy beam of electrons and you separate out the ions by focusing the ions in a beam which is then bent by a magnetic field. So what is done is you allow these particles to come through a repeller electrode. So this is where your electrode is. So that's your electrical field. And you allow them to pass through this filament and accelerate it through the accelerating slits. And then that is subjected to the magnetic field. So the accelerated ions are going to go through, and then depending on the mass of how focused or unfocused they are, they could either kind of hit and be just fly away essentially, or they would be focused and then they would go to the detector, and that is the peak that would that is the ion that will be detected by your detector. So this detection is basically done electronically. This is an electronic. That means there is a computer that is hooked up, which will analyze and store the data. So the mass spectrometer here essentially has the heart of the spectrometer is the ion source. So this part is where majority of your stuff is happening. So once again, molecules of the sample, which I have in this case shown by the little black dots, they are being bombarded by the electrons. So that's what's happening over here. Let's just say electron bombardment. Electron bombardment. So the ionization is essentially occurring over here. And that is happening because you have the heated filament. And after this electron impact occurs, essentially the gas or the volatile liquid samples, those are allowed to go through the magnetic field. So one can say that past this filament, maybe let's past this point. Here, what you see, this part in green, that is actually a positively charged species. Positively charged species. And since they are positively charged, they are going to be repelled and pushed away, whereas the anions, they are going to be attracted to it. So these are accelerated, they are repelled, they are accelerated towards the other electrode, which has the slits. So those are the slits that I talked about earlier. And the ions sort of pass through them as a beam. Some of these ions, they fragment into smaller cations or neutral fragments. Like I said, neutral fragments will not show up, the cations will show up. And so in a mass spec, you don't just see like one peak. No, that's not what you see. You might see several peaks and then maybe a larger peak, which I'll talk about in a second. But you see several peaks, and some of those peaks would just belong to the fragment ion. So the magnetic field deflects the ion beam in an arc whose radius is inversely proportional to the mass of each ion. So lighter ions are deflected more, heavier ions are going to be deflected less. So one can say that the one that is getting closer to this side, those are going to be your lighter ions. The ones that are kind of on this side, they're less deflected, so those are your heavy ions, and the ones that are kind of going through are the ones that are going to be detected, and those two are under vacuum. So keep that in mind, that we are maintaining that vacuum at all times. So when a high energy electron basically collides with the molecules, it is going to ionize the molecule, and it's going to basically knock off one of the molecular electrons, which could be bonding, it could be non-bonding, and it basically leaves behind a molecular ion. So just to kind of give you a flavor for that, let's say I had a molecule and I'm hitting that with electrons. Essentially, this electron is going to take away one of the electrons. It's just a result of the speed with which we are hitting, and what you end up getting is what is called as a molecular cation radical, sometimes also just molecular ion. This can either form some neutral fragment. It can take away a neutral fragment, or you can have another result of that, which is that the M plus gives you a neutral fragment, but the electron has then gone with the fragment part. So both of those are a possibility, and both of those are going to be detected on your mass spec. So again, you will leave behind a molecular ion, or you can see any of the fragment ions. Both of those are a possibility. And like I said, molecular ion is a radical cation. The fragment ions, however, could be radical cations, or just could be carbocations. So either this M plus or M plus with a radical. These two are the ones that are going to be detected on a mass spec. Now, as we go through a mass spec and we have gotten our mass spectrograph, what can be conceived from there? What are the various different fragments that you can see? Let's talk about that a little bit. What you have on the x-axis is an M by Z. What you have on the y-axis is an abundance. And you could get a lot of peaks. So let's say you have 0 here, 10, 20, 30, 40, 50. And suppose I have my molecule is, let's say my molecule is propane. Okay, propane is my molecule, so that's C3H8, and that means 3 times 12 plus 8, which is 44, is your molecular mass. What does that mean? That means that you will see a molecular ion, so this is 45, you will see a molecular ion, maybe somewhere around here. That may or may not be the largest peak. You might see, in the case of propane, you will see a peak at 29. That didn't come out straight. Let's try again. Better. And that will be of your highest intensity. The maximum that you see on the x-axis is your molecular ion that also gives you your molecular mass. For molecular mass, the maximum that you get, which is the 100%, the maximum that you get there is what is called as the base peak, and that is the peak which corresponds to the most stable carbocation. And so this is the maximum abundance. The base peak is the one that you get which is a result of the maximum abundance that you have. So it's the most stable carbocation. And it may or may not be your molecular ion. Sometimes it is. On the other hand, if you think about the molecular ion peak, that usually reflects the molecular mass of the material. Now one might say, well, on the x-axis didn't we have like an m by z? But this z usually has a charge of 1. It's kind of difficult to get a cation which is doubly charged. So one can say that the m by z is nothing but m. It's the mass. Now, one thing to think about here is that when you think about stable organic compounds, they usually will have even number of total electrons because they reflect the fact that electrons are occupying the atomic and the molecular orbitals in pairs. Recall from the atomic and the molecular orbital theory that for every alpha spin there is a beta spin, right? Hopefully everybody remembers that. So now when you took the time to take the molecule and you hit it, you bombarded it with an electron and you removed an electron from the molecule, which gave this ion or this molecular ionic species, the total electron count now becomes an odd number. And at that point of time, we will refer to such ions as radical cation. So the radical cation does have odd number of electrons. So it's important to realize that the molecular ion in a mass spec is always a radical cation. So it always will have essentially odd number of electrons. But a fragment ion may either be even electron cation or an odd electron radical cation, depending on what is the fragment that has been lost. So keep in mind that the M plus with a radical, that is going to have an odd number of electron, but the fragments that are generated could be odd or even number of electrons. Usually what we see, what happens is that when the fragmentation occurs, the bonds cleave in such a manner that a neutral radical is produced, so the odd electron goes away that way, and a cation having an even number of electrons is generated. Okay, so at this point of time, I want to remind you of the DOE, the degree of unsaturation, and the nitrogen rule that you may remember. Whenever you have to determine the degree of unsaturation, which basically means that you could have rings or you could have double bonds or triple bonds in the molecule, that can be determined by looking at the number of carbon atoms. From that, you're supposed to subtract half the number of hydrogen atoms. You have to add half the number of nitrogens, subtract half the number of halogens, and add one, and that will give you the degree of unsaturation. And if the molecular formula of an ion is known, then we can use the DOU to determine whether the species that you will get for the molecular ion, whether that will be an even or an odd electron species. We would be able to do that. If your molecular ion is going to be an odd electron ion, then the DOU comes out to be a whole number. On the other hand, if it is an even electron ion, then it is going to end in a half, like a 5.5 type of thing. And the other thing that I wanted to say was the nitrogen rule. Nitrogen rule. According to which compounds containing elements that are common in organic chemistry, so carbon, hydrogen, oxygen, silicon at times, phosphorus, nitrogen, of course. We are referring to those. So for a molecule to have an odd numbered molecular weight, it must contain odd number of nitrogen atoms. So if you have, let's say 87, that means it can contain 1, 3, 5 nitrogen atoms. On the other hand, if a molecule contains an even number of nitrogen atoms, so 2 or sometimes no nitrogen atoms, so even or no nitrogen atoms, that would mean that it has even molecular weight. If it's an odd number, that would mean that it has odd number of nitrogen atoms. And this fact basically arises from the fact that even though nitrogen has an even mass, it has an odd valency. That means it can make only 3 bonds, not 4, as you would see in case of a carbon. Now, usually you would see that MS would be hooked up to GC. So what can be done is that you have like a GC component and the fragments that you're getting. So let's say this is your GC chromatogram, this is your first, this is your second, this is the third, and this then gets sent to the MS. So you find out the mass of the first fragment, the second fragment, and the third fragment. So not only are you determining the number of components that are present in a reaction mixture, in addition to that, you can actually determine the mass of each of those. And so if you are able to determine the molecular ion, which if matches to the molecular ion of your product, you can tell which of the 3 peaks is the pertinent peak that you should go after and purify and determine to be your product. So GCMS is actually a very, very important tool in identifying the particular component of interest for your reaction, for a certain reaction. Now, realize when you're applying the nitrogen rule, again, nitrogen rule states that if you have an odd mass of odd molecular mass, then that means that you have an odd number of nitrogen atoms, and if you have an even molecular mass, that basically will have even or no nitrogen atoms. And this kind of stems from the fact that nitrogen has an even atomic mass of 14, but it bonds with 3 other atoms in its most stable form. And so an even AMU plus an odd number of substituents will give you an overall odd molecular mass. On the other hand, if you're considering an even AMU and an even number of substituents, then it is going to give you an overall even mass. So for instance, what we are saying is if you have, let's say, a nitrogen which is bonded to maybe 2 methyls and 1 ethyl group. So if you were to sort of count the whole thing, you would say this is CH3, this is CH3, this is CH2, and this is CH3. So you have 15 from here, 15 from here, 15 from here, 14 from here, and 14 from here. So that's 15, 15, and 15. That's 45 plus 14 and 14. That's 28. That will give you 13 and 73. And that's your AMU. That's your molar mass. Now, notice this is odd molecular mass, and it contains only 1 nitrogen atom because nitrogen is making only 3 bonds. Now, if you had 2 nitrogen atoms in a certain case, so let's just change the structure a bit. So if you have maybe a hydrogen here, or let's keep that, so CH3, CH2, CH2, and then nitrogen, and then CH3, and then CH3. Now, since it has 2 nitrogens, that would automatically mean that it is going to be an even molecular mass in this case. So 15, 15, 15, and 15, that gives you 60. 2 nitrogens will give you 28. 2 CH2s will give you 28 as well. So it is going to end in 8, and 8 is 16. That will be a even number. So so whenever you have an even number of nitrogens or no nitrogens, that will give you an even molecular mass. On the other hand, you will have an odd molecular mass that reflects of odd number of nitrogen atoms. So for instance, if you were to look at the mass of this compound, I have nitrogen, I put 2 methyls and 1 ethyl. And we have 73 AMU. We just did that. And M by Z and the abundance. So you're going from 0, 15, 30, maybe 45, 60, and 75. So that would mean somewhere over here, 73 will be your molecular ion. And then as it loses fragments, it's going to, so let's say it lost the methyl group, or the methyl group here, or the methyl, essentially it's now going to give you all all even number of fragments. So one thing that one can perhaps see, even fragments coming from odd molecular ion, and the moment you see that, you would say that it will contain odd number of nitrogen atoms. So sometimes, depending on, it's a handy rule to think about if you're not given a molecular formula, but you're only given pieces of other forms of spectroscopy. You can still use it to determine your overall structure. So again, odd electron molar masses, if they generate odd electron ions, they may fragment either to odd or even electron ions, but even electron ions will only give other even electron ions from the perspective of mass spec. Let's consider isotopes in mass spec. The only thing that I would want to say here is that depending on the mass spec that you get, actually, depending on the mass spec and the kind of pattern that you get. So for example, if you have bromine, the fragments of bromine, the natural abundance of bromine, the bromine 78 and the bromine 80 are about 1:1 in nature. That's how they exist. So in case of the mass spec, if it does contain bromine, you will always see an M, and then you will always see an M plus 2, both which will be of the same height because it's 50-50. On the other hand, once that bromine is lost, the abundance is going to change. But bromine containing compounds will have this very typical pattern. So if you know something about bromine, or if you know something about chlorine, which has a ratio of M and M plus 2, so chlorine 35 and chlorine 37 being in the ratio 3:1. So that's one thing about chlorine. And so you can say that looking at the abundance of the isotopes, one can predict if there is a specific type of atom or a specific type of isotope which is present in a molecule or not. And so it is to our benefit to use these kind of studies for isotope incorporation, which is used to determine, in biosynthesis. Biosynthesis is a tool, is a science that people use to study, to figure out how a certain animal or a certain compound is generated in the body, for instance. So again, to reiterate, when you run a mass spec molecular ion, that's the maximum that you usually see for the x-axis, highest that you see on the y-axis, which is the abundance. That's your base peak. Looking at the pattern, one can talk about the isotopes. That's another thing. Nitrogen rule could be used to figure out the number of nitrogen atoms, and depending on whether it's an odd number or an even number, you can make predictions on the molecular ion, and hence go from there to determine the structure. But the net idea ultimately is that mass spec is used to determine the molecular mass of a certain compound. So if you're given, let's say, 2 isomers, mass spec is probably not the best method to determine that just on the basis of molecular ion peak, until and unless there are differences within the structure that the fragmentation pattern will now change. But realize, in terms of when you compare this to an IR is a much stronger method in that sense, because it gives you some information about the structure, the functionality. But ultimately, the most powerful spectroscopic tool that we have is NMR, nuclear magnetic resonance, which is the last one of all the spectroscopies and the most powerful one.